Welcome to our presentation of DKM, dense kernelized feature matching for geometry estimation. I'm Johan. Let's get started. In dense feature matching, we want to find all pixel pairs that correspond to the same 3D point. Once we have these matches, we can estimate geometry. Our intuition is that dense approaches, which output more matches, should lead to better pose estimation. However, surprisingly, we found that dense methods actually underperform at geometry estimation, and the question is why? And, importantly, is this a fundamental limitation of dense methods? Luckily, it turns out the answer is no. Our dense matcher DKM outperforms sparse methods on geometry estimation. In the bottom row, we have visualized a bunch of beautiful warps from our matcher DKM. Stick around for the full presentation to find out how we got these results. Let's first take a step back. What is the reason that previous dense methods underperform at geometry estimation? Let's first revisit how dense matching is typically formulated. First, we compute feature pyramids from the two images. This is composed of coarse features and fine features. Second, the coarse features are fed into a global matcher. This global matcher produces a coarse warp and a certainty estimate. However, this is not precise enough for the final estimation stage, so we need a warp refinement stage. In this stage, the warp and certainty is refined to improve the precision. We have visualized this refined warp and certainty by backward warping between the images using the estimated warp. We then multiply with the estimated certainty to see where the network is certain about its predictions. After this stage, fourth, we sample matches to feed into some estimation pipeline. And finally, fifth, the estimator we have chosen estimates the two-view geometry. Note that in this paper we focus on the green stages and leave the gray stages unchanged. So let's find out the reason that dense methods fail. We found two important reasons that dense matching fails. One, if the global matching stage fails, large regions will be unmatched. This is bad as we lose match diversity, which is critical for robust estimates. Two, even successful matches are not precise enough in previous methods. Estimation requires extreme subpixel precision, which previous dense methods could not provide. The other main reason is that previous dense methods are overconfident and use simplistic sampling approaches. So, there seems to be no fundamental reason that dense methods underperform on geometry estimation. Rather, there are multiple solvable issues which all degrade performance. So what's left is simply to solve all these issues. We start by making a stronger global matcher to prevent global matching failures. To do this, we explicitly formulate global matching as a probabilistic regression problem, mapping from features to coordinates. We solve this problem with Gaussian process regression. Importantly, to retain multimodality, we use coordinate embeddings. Since we need the warp at the end, we decode the embeddings with an embedding decoder. The details are provided in the paper. Read section 3.2. The equations on the bottom of the slides describes how we can get a posterior mean and variance of coordinate embeddings chi given a kernel on the features. To fix the lack of precision, we improve the refinement stage. First, we improve the input representation by stacking feature maps. Second, we found that the refiner architecture could be improved by using large stepwise kernel convolution. The architecture is detailed on the right of the slide. At the bottom, you can see a qualitative improvement in the warp accuracy compared to previous approaches. Further, we improve the certainty estimation and the match sampling strategy. First, we simply let the model predict whether the ground truth multi-view stereo depths are consistent between views. The equation used is given in the top right of the slide. We found that this greatly improved confidence estimates compared to previous dense approaches. Second, for sampling, we reweigh the matches with the inverse of a kernel density estimate, as described by the equation in the middle right of the slide. This has the effect of diversifying samples across the scene, which we found to improve estimation. We found that when adding our improvements together, we significantly outperform sparse and dense methods for geometry estimation. So it seems like there was no fundamental issue. I'd like to end by showing some qualitative examples and our takeaways. We believe dense matching is the future for geometry estimation and are excited to see further research in this area. Please check out our code at github.com/pashcat/DKM. Thanks for listening and have a nice day.